Now let us do the analysis of binary search. So for the same list, if you observe, when we have searched for various keys, every time mid value was 7. Obviously 0 to 14 middle is 7 only. Initially low was here and high was here and we were getting mid. This is mid. So always we were getting mid at 7. So if suppose we are searching for a key 27, then in first comparison only our search should terminate that key is found. So it means that key value at index 7, the key value 27 can be found in just one single comparison. And next we were searching for the element on the left hand side. So high was here and mid was this one. So for the left hand side, middle element was 15, the index was always 3. So on the left hand side, middle one is index is 3 and the element is 15. Then on that side if we check, if we are checking for an element on right hand side, then the low will be this one and high will be this one, and this we will get it as middle, that is index 11 and the element is 37. Index 11 and element is 37. So it means if you are searching for 37, then it will be found just in two comparison. First time we will check for index 7, that is 27, element is greater 37, go on the right side, take the mid, we get this mid, element will be found in two comparison. So from this list, this will be found in one comparison and this will be found in two comparison and this also in two comparison. What about remaining? So I will quickly write down about the remaining one. If I take the left hand side list, that is from 0 to 6, the middle element was 3. Then on the left hand side, if I take this list, then the middle will be 8, that is index 1. So this will be index 1 and element 8. Then on the right hand side, this list, this is the middle one, index 5. So here right hand side is index 5 and the element is 21. For this 8, left hand side is 0 and element 4, right hand side is index 2, element is 1. So if I remove this, you can see that this is on the left hand side. So this is on the left hand side, this is on the right hand side. So for this middle one is index 1, left side is 0, right side is 2. So this will be 0 and this will be 2. And the element here is 4 and element here is 10. Now this side, left hand side is 4 and element is 18, right hand side is 6, element is 24. So this is 18 and this is 24. Now similarly I'll prepare for the right hand side also. So for right hand side list, leaving this as middle, this is the right hand side and this is the mid one. So 11. Then for these three elements, this is the mid one. So left hand side is index 9 and its left is index 8 and its right is index 10. So the elements are 33, 29 and 34. And on its right hand side, these are the three elements, middle one is 13. So this is 13 and on its left hand side is 12, right hand side is 14. And the elements are 39 and this is 41 and this is 43. So this is a tracing tree we got based on the working of binary search. So we will discuss from this tree. Now if you observe, 21.7 can be found just in one comparison. Then 15 and 37 can be found in two comparisons. Means if the element is 15, we go on the left hand side. If the element is 37, we go on the right hand side. These elements which are at level 3, these will be found in 3 comparisons. And these elements will be found in 4 comparisons. So maximum how many comparisons are required? 4 comparisons are required for searching, not more than 4. Whether the element is in the beginning of a list or at the end part of a list, wherever the element is, maximum comparison required for searching are 4. So from the tree you can clearly see that at most 4 comparison to reach any element. So the number of comparison depends on height of a tree. This is a tracing tree, so the height of this tracing tree is log n. So the time taken will be dependent on the number of comparisons, and the number of comparisons are at most log n. So the time taken for searching in binary search is log n. So minimum time is, if you are searching for an element which is present in the middle, so the minimum time is order of 1, so you can say this is the best case. And what is the maximum time taken if the element is present here? According to this tree, if they are present in a leaf, or those elements which are reachable, they are found at fourth comparison. So the maximum time is order of log n. This is the best case time. This is the worst case time. So best case time of binary search is order of 1, and the worst case time of binary search is log n. So this was about successful search. What about unsuccessful search? Let us see. If I am searching for any element that is smaller than 4, then what happens? I'll check here. 4 is smaller than this, 4 is smaller than this, 4 is smaller than this, 4 is smaller than this also. So it will end up on the left hand side. If I am searching for any element which is present in between 4 and 8, then what happens? Let us see. 4 and 8. Let us take one element 7 and see what happens. 7 is smaller than this, 7 is smaller than this, 7 is smaller than this, 7 is greater than that. So it will end up here. So it means this node, the one which is a squared node that I am showing or representing unsuccessful searches. So this node is representing all those elements which are smaller than 4, which is not there in the list. And this represent all the elements that are in between 4 and 8. So those are 5, 6 and 7. These 3 elements it is representing. Similarly, we can represent the nodes here for all those elements which are not there in the list. So if you are searching for any element, then we say that the search will terminate at these nodes. So for unsuccessful search, this shows that it reaches at the end of a tree always. So the time taken in unsuccessful search is always order of log n. So successful search, minimum is 1, maximum is log n. For unsuccessful search, it's always order of log n. Next, we have also seen a recursive procedure. So that recursive procedure also behaves in the same way. First, it will go in the middle. If the element is small, then it will search on the left hand side, that is in the left subtree. If it is greater, it will search in the right subtree. Then again, it will call itself recursively on the left sublist or right sublist. So the maximum number of comparisons it may be making, or the maximum calls it will be making, will be at most 4. And if the element is not found, then it will be a 5th call. It will stop at 5th call if the element is not found. So the number of calls a recursive algorithm will make depends on the height of a tree. So that is log n. So whether you write a iterative procedure or recursive procedure, the time is log n. So how binary search is log n, I have shown you. Now I'll show you using some other method how binary search is log n. See, we have total 15 elements here, 0 to 14. 15. 15 is not in powers of 2, so I will just make it round as 16. Okay, to explain you how it is log n, I'll take it as powers of 2, that is 16. Assume that the number of elements are 16. Number of elements are 16. So how binary search is working? 16 it has divided by 2. So 8 elements this side, 8 elements that side. Assume this one. So 8 elements we are getting. Actually here we will be getting 7 elements, but as we have taken it as 16, so 8 on this side, 8 on this side. If you are searching on the left side or searching on the right hand side, again divided by 2. Then again divided by 2. So how long this can get divided? Until you are left with just one number. If there is only one number, beyond that you cannot proceed because there are no numbers. So last one, it should stop at 1. So 16 divided by 2, divided by 2 and divided by 2. So how many times I should divide 16 by 2 such that it reaches 1? So I should divide 16 by 2 power 4 so that it reaches 1. So that's all. So it means this list will be divided 4 times to reach at last one single elements. See, these were total 16 elements, assume this, half, then this half, then this half, then we got just one element. Either our search stops here or at last it will stop here. So this is 4. So the answer we got it as 4. So how do you calculate that? 16, how many times it should be divided by 2 to get the answer 1? It's nothing but 16 is equals to 2 power 4. So 4, this is nothing but 2 power 4 is equals to 16, and 4 is log 16 base 2. So actually inverse of power is log. Inverse of power is log. So 2 power 4 power is 16. Then how much is 4? Is log 16 base 2. So log n. So this means the time taken is log n base 2. So when I have made it in powers of 2, so I can explain you here. Otherwise 15 means 15 by 2, 7. So we will not get exactly in powers of 2. So I have taken an example as 16. So from 16 we can observe that log n base 2. So here we can say that whatever the number of elements you have, n plus 1, then log base 2. Exact answer, we got this one. 15 elements were there, then in that you add 116, so log n base 2. So exact formula is log n base 2, and so exact formula is log n plus 1 base 2. So but roughly we take it as log n. So because the polynomial degree is log n, so we take it as log n. Then one more thing. If there are more than 15 elements, then definitely the number of comparison will increase by 1, because that is the maximum number for which we require 4 comparisons. Otherwise, if the number is greater, then it will be 5 comparisons. So that I can show you here. That is, if you have 16 elements, then 16 plus 1 log base 2 is nothing but log 17 base 2. So this will be 4 point something. So suppose 4.2, then this should be taken as 5. So this value should be taken as seal. Log base 2 n plus 1 should be taken as seal. So I have shown you from the tracing tree, and also I have given you the idea, just the idea. This is not the method or an approach, just I have given you the idea how it is log n. Because every time getting divided by 2, so when something is successive division is nothing but log. Successive multiplication is power. That's all about binary search and its analysis.